আমার প্রিয় শিক্ষার্থীবৃন্দ, সহকর্মীবৃন্দ এবং যে সকল দর্শক এই মুহূর্তে পৃথিবীর যে যে সব জায়গা থেকে যে আমাদের এই অনুষ্ঠানটা দেখছেন, আপনাদের সকলকে আমাদের এই ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনারে স্বাগতম। শুভ সন্ধ্যা এবং যে যেখানে আছেন তাদেরকে শুভ সকাল বা শুভ বিকাল। আশা করি আপনারা সকলে ভালো আছেন। আমরা এই বিশ্ব করোনা মহামারীর সময়ে আছি। আমাদেরকে স্বাস্থ্যবিধি মেনে সবকিছু জীবন যাপন করতে হচ্ছে। এর মধ্যে আমাদেরকে কিন্তু একাডেমিক কার্যক্রমও চালিয়ে যেতে হচ্ছে অনলাইন, এবং কোনো ক্ষেত্রে হয়তো সামনাসামনি আমরা নিতে পারছি, আবার মাঝে মাঝে বন্ধ হয়ে যাচ্ছে। তো আমরা এই গত ২ বছর ধরে একটা জিনিস আমরা কন্টিনিউ করে যাচ্ছি, আমাদের যে ওয়েবিনারটা, এবং আজকে আমাদের ২৭৩তম আজকে পর্ব, এবং আজকে পর্বে আমরা যাকে পেয়েছি তাকে নিয়ে আমরা গর্ব করি। আমরা আমাদের সাথে ইতিমধ্যে পেয়েছি ডক্টর নাবিল ইকবাল স্যারকে। স্যার এখন কর্মরত আছে অ্যাসোসিয়েট প্রফেসর হিসেবে ম্যাথমেটিক্যাল অ্যান্ড থিওরিটিক্যাল পার্টিকেল ফিজিক্স, ডারহাম ইউনিভার্সিটি। স্যার ইতিমধ্যে আমাদের সাথে সংযুক্ত হয়েছেন। আমি স্যারকে আমাদের ওয়েবিনারে স্বাগতম জানাই। স্যার, আপনাকে স্বাগতম এবং অনেক অনেক ধন্যবাদ যে আমাদেরকে আপনার ব্যস্ত সময় থেকে সময় দিয়েছেন। তো প্রিয় শিক্ষার্থী এবং যারা দেখছেন তাদের উদ্দেশ্যে বলবো যে আপনারা চাইলে আমাদের সাথে সংযুক্ত হতে পারবেন। আমি আমাদের লিঙ্কটা কমেন্ট সেকশনে দিয়ে দেব, এবং আপনারা আপনাদের যে কোনো প্রশ্ন আমাদের নাবিল স্যারকে করতে পারবেন কমেন্টের মাধ্যমে। তো স্যার, আপনি চাইলে শুরু করতে পারেন। ধন্যবাদ আবার আপনাকে। You can start, sir.
ধন্যবাদ। Thank you. So hello, আমার নাম নাবিল। আমার টকটা ইংলিশে হবে। আমি খুবই সরি ইংলিশে করতে হচ্ছে, because সব স্লাইডগুলো ইংলিশে, এবং ফিজিক্স নিয়ে যখন কথা বলি তখন আমার ইংলিশেই করতে হয়। আমি খুবই সরি এটার জন্য, বাট প্লিজ আপনারা বাংলায় প্রশ্ন করতে পারেন, আমি বাংলায় উত্তর দেওয়ার চেষ্টা করব। So let me get started. The title of my talk is Symmetries and Strings to Hydrodynamics. শুনে যাচ্ছে ঠিক মতো? আমাকে শুনতে পাচ্ছ সবাই?
জি স্যার, জি ক্লিয়ার।
Okay, so আমার নাম নাবিল, and as was just said, I'm at Durham University. So at this moment, actually, I'm currently on strike from Durham University. This is a big thing. I'll tell you a bit about it later, but basically at this moment in 68 universities in the UK, many thousands of lecturers are on strike. I'll mention this at the end, but I felt like I had to explain this while explaining why I have this written here, that I'm currently on strike from Durham University. Okay, so let's get started. So to begin, I'm going to tell you about the setup. I'm going to tell you a few different things about symmetries, about string theory, and about quantum field theory, but I want to begin in a very, very, very general way. Okay? So I want to talk about the goal of physics, and the goal of physics is to understand nature. So when I first started learning physics, I was very, very interested in understanding very, very small things, microscopic constituents. Okay? So let me explain what I mean. So imagine you have a glass of water. Okay? So water is something it's a big object, and water, like everyone knows, is made of smaller molecules. Water is made of H2O molecules. So here's an O and there's two H's. And each of these H2O molecules is made up of there's oxygen and then there's hydrogen. And each of the molecules is made up of smaller atoms. So here's an atom. The atom has protons and electrons moving around it and going around and around. And each of these protons is made up of smaller things, right? Each proton looks something like this in the inside. A proton is made up of smaller things called quarks. And the quarks are held together by gluons that hold everything together. And this keeps on going and going and going. The quarks are made of smaller things, probably, and so on and so forth, until finally, at the very smallest scales, everything is made of string theory, in some sense. And you see, when I first started learning physics, what I thought is that if I just understand the smallest thing, if I understand the strings, then I'll understand everything else that there is to understand. But this isn't actually true, okay? If you want to describe a system, what you should do is you should use the appropriate theory, not the most microscopic one. In other words, if you want to understand a glass of water, which is roughly 1 centimeter big, you should use the theory of hydrodynamics. If you want to understand other things, you should use other theories. So for example, if you want to understand the protons, you should use quantum chromodynamics. If you want to understand a black hole, you should use general relativity. If you want to understand the whole universe, you should use general relativity in a different regime. And finally, if you want to understand the absolute smallest of things, you should use string theory. So this idea that your theoretical description of something should be suited to the length scale of interest, this idea is called effective theory. Okay. So, in other words, if you want to understand something, you should try to construct an effective theory that describes it. But what are the actual principles that we use to construct an effective theory? So there's an absolutely crucial concept here, which is called symmetry. Okay. Most things in nature have certain symmetries, and those symmetries really tell you how to build an effective theory that describes them. So let me begin by giving you some examples. So for example, suppose you have a conserved number of particles in a box. Okay. So here's a box and here are some particles in there. The particle number is conserved, which means that there is an equation that looks like this that tells you the particle number is conserved. If you have a particle density, the time derivative of the particle density is equal to the divergence of the particle number current. What this just tells you is you cannot lose particles. Okay? The particle number goes down, it's because they've moved somewhere else. Now, in quantum mechanics, we know that particles are actually associated with fields. Okay? And from classical mechanics, you might know about Noether's theorem. Noether's theorem tells you that conserved quantities come from symmetries. In other words, every time you have a conservation law, that comes from some sort of a symmetry of your system. In the simplest case, that the particle number is conserved, this particle number conservation comes from phase rotations of your system. In other words, I have this field phi, which is a complex number, and the symmetry says that if you rotate your field by multiplying it by a phase, everything is invariant under that rotation, and by Noether's theorem, this gives you a conserved particle number. So this is a really important concept that I think most of you have probably learned about earlier in your study of physics. So the really interesting thing is that you see symmetry tells you how to build your effective theory. So say you want to describe some sort of effective theory for these particles, okay? So what you start doing is you start to write down a theory that respects your symmetries. So some of you might have seen equations like this, some of you might have not. It's not terribly important what the equations say. But the basic idea is that, for example, you are allowed to add a term like phi, magnitude of phi squared, to the power fourth to your effective theory. What that tells you is that you can have two particles coming in and scattering off of each other and two particles coming out, and that's allowed because the particle number is conserved. On the other hand, this kind of thing is not allowed. You can't have two particles coming in and only one particle coming out because that breaks particle number. Particle number is no longer conserved. If two come in, only one come out. And mathematically, that is encoded in the idea that you cannot add a term like this to your effective theory. Here, phi and phi dagger both eat two particles, and phi having one coming out. This thing is not invariant under the symmetry. You can see that if you do the symmetry rotation, because you have one phi dagger and one phi, this whole thing is not invariant because it represents a process that is not allowed by the symmetry. Okay, so these are some basic ideas about symmetries and effective theories. So now let me tell you something more about symmetries. Symmetries can sometimes spontaneously break. So let me explain what I mean by this. Imagine you have a bunch of particles in a box, okay? So they're doing their thing, they're just moving around and bouncing. In that case, you will have some field associated with this configuration, and the field is going to do some crazy thing. It's going to wiggle around in some crazy way, and the phase of this field is going to change in some dramatic way, okay? This situation where everything is just wiggling around in some manner is what's called normal, or we say the symmetry is unbroken. To see why this is called unbroken, let me compare it to something else. Here is something that can also happen. You might have that the field living in this box, all of the phases in this field, all of these degrees of freedom are all lined up in a very special manner. In that case, we say the symmetry is spontaneously broken. Okay. And what that means is, you see, if you do the symmetry operation, if you try to rotate this guy, then all of these will move together in a slightly different configuration, and it will look different than before. So in this case, we say the symmetry is spontaneously broken. In this case, we say the symmetry is unbroken. Okay. So in this case, the symmetry is spontaneously broken. All the phases are lined up, and it turns out that the quantum state of all of these particles is very special. We typically call this a superfluid. It's a very different phase of matter with its own effective theory. Okay. So I began by discussing some sort of fancy example with quantum mechanics, but the same idea is true for all different effective theories. For example, hydrodynamics is an effective theory. Let me think about what this means. Imagine you have a system where you have momentum conservation. Okay? Momentum conservation comes from the fact that you have translational symmetry. In other words, you can take your system and move it slightly and everything remains the same. If you combine momentum conservation with finite temperature, with the idea that things are wiggling and bouncing around, then this combination of things is enough to tell you how to think about the effective theory of hydrodynamics. So from combining these two ideas in the right way, you get everything that you know and love from hydrodynamics. In other words, you get the Navier-Stokes equations, you get dissipation, and so on. All of that comes from combining just the simple idea of momentum conservation with the concept that things can be at finite temperature. Okay. So what happens if you spontaneously break these symmetries in hydrodynamics? So for example, we have a translational symmetry for a liquid in that you can move this translation, you can move this box a little bit and everything stays the same. If this symmetry is unbroken, then this is sort of the normal phase and we call this a liquid. But what can happen is the translational symmetry can be spontaneously broken. When that happens, it's a very dramatic thing. Translational symmetry being spontaneously broken means that the molecules all form a rigid, regular order. And in fact, we then call this a solid. Okay? So the real difference between a solid and a liquid is that a solid has a spontaneously broken translational symmetry, because if you translate it a little bit, it looks different. But the liquid does not. That is the real difference between a liquid and a solid. So this idea that the different phases of matter are defined by different patterns of broken and unbroken symmetry is called the Landau paradigm. This is Landau, and this is what he told us, that the different phases of matter can be understood by what symmetries they break or do not break. So this is a really dramatic idea, and maybe this is a good time to pause. Are there any questions about this? প্রশ্ন জিজ্ঞেস করতে পারো, বাংলায় করতে পারো।
স্যার এখনো কোনো প্রশ্ন পাইনি।
প্রশ্ন পাইনি। Great, thank you. Okay, তাহলে আমি কথা বলে যাচ্ছি। So, this is the Landau paradigm. Now, everything we did so far involved having particles in a box. Okay, we had a bunch of particles in a box, and they did their thing. But you know, in life, we sometimes have more things than just particles, right? So here's something that might happen. You might have conserved strings and not particles. So this might sound like a very fancy thing. You know, strings is some fancy thing from string theory. But actually, that's not true. Strings exist in sort of very mundane physical systems. So for example, you have all studied Maxwell's equations, okay? And if you studied Maxwell's equations, then you know about strings. You can have magnetic flux lines. So here's a picture that could be taken from any of your textbooks. In this picture, here we have a solenoid, and this solenoid has magnetic field lines that go through it. Okay, so here's some magnetic field lines. And these magnetic field lines don't end. Magnetic field lines never end, they just always go on forever. And what that means is they are strings that are conserved. Okay? Because they don't end in space or in time, that means there's a conserved quantity associated with this. Now, if you study classical mechanics, you will know that from Noether's theorem, a conserved quantity means that there is some sort of a symmetry involved. So because you have this symmetry, because you have this conserved quantity, you should ask, what is the symmetry principle behind this conserved quantity? So it turns out the symmetry principle behind this has only very recently been understood, and it is motivated by non-abelian gauge theory. If you know what non-abelian gauge theory is, that's great. If you don't worry about it. Non-abelian gauge theory is some fancy thing that describes, the elementary particles in our universe. But the main point for this slide is just to tell us that these scientists, Gallardo, Kapustin, Seiberg, and Willett, in 2014, they finally understood the symmetry principle by trying to understand rather intricate problems in non-abelian gauge theory. In this talk, I am going to try to tell you how these fancy symmetries are relevant for more mundane things like hydrodynamics and Maxwell's equations. So the main point here is that a higher form symmetry implies the conservation of string number. Any theory, including Maxwell electromagnetism, that has such a conserved string density must have such a higher form symmetry. So this sort of thing is also called a generalized global symmetry. Okay, so what does this mean? What is a higher form symmetry? So a higher form symmetry is sort of a fancier version of an ordinary symmetry. So let me now show you what this means. So if you have a normal conserved current, that will come with a density and a particle current. The density tells you how many particles you have in a small volume, and the particle current is a vector because it tells you how the particles move in space and time. So here's a picture. You have some particles in a box, and there's some density and there's some current. If they're moving, there'd be some current. A higher form symmetry is a little bit different. For a higher form symmetry, you don't just have a normal current, you have a two-index tensor, in other words, an object with two indices, where these indices are antisymmetric. But what does this mean? This means that the density already has a vector index, meaning the density already points in one direction. That's because if you have a bunch of strings, the strings don't just sit there, the strings point in some direction, and I have to tell you which direction those strings are pointing in. Similarly, if you have some strings pointing in the z direction, then those strings can move in the y direction. So the current associated with string movement has two indices, because I have to tell you if some current pointing in the z direction is moving in the y direction, and so on and so forth. Okay. So here is a picture of a bunch of strings, and they're doing their thing. They can move in space and time and move in some manner. So the conservation of this particle current is given by a formula that looks like this: d mu j mu equals to 0. Similarly, the conservation of string number is given by an equation that looks like this: partial mu of j mu nu equals to 0. It means the string number is conserved. Now, what about charged objects? I started this talk by giving you the example of having some field and how you could rotate it by acting with a phase rotation on this. So the charged object there was a local operator. It's a local operator because if you want to create a particle at some point, you have to tell me, where do I create this particle? You act with a local operator at this point, and that creates a particle there. Strings are a little bit different. If you want to create a string, you have to tell me what this string is doing at some moment in time. And in the quantum theory, what that means is you act with a line operator. This line operator will then create a string, and the string will then go off and do its thing. And in fancy quantum field theory language, what that means is the object that is charged under this higher form symmetry is a line operator and not a point operator. Okay. So let me now give you an example of a theory that has one of these fancy symmetries. So here are the equations of 4D Maxwell electrodynamics, which I've written in relativistic notation. You might have seen this, and you might not have. Those of you who study special relativity will probably have seen this way of writing Maxwell's equations. So these are the normal equations of Maxwell electrodynamics. And let me now tell you about the string density. The string density in Maxwell electrodynamics looks like this. You take your F and you act on it with the epsilon tensor, and you get some object j mu nu. And this object is conserved. You can check this easily for yourself from these equations if you're familiar with this relativistic notation. But what this basically just means is that magnetic field lines don't end, and this current j mu nu just counts the magnetic flux density. Okay, that is the role of j mu nu in life, and the higher form symmetry is just telling us that magnetic field lines don't end. So that's the basic idea. And now in the second part of this talk, I want to tell you about a few applications of this idea. Let me again pause and just ask, does anyone have any questions at all?
Not yet, sir. এখনো
Not yet.
আসেনি।
Question. Okay. Yes.
Okay.
Then I'll pause for 1 second just to give someone an opportunity, and if not, I'll just keep going. Okay. So now what we're going to do is try to apply this idea of higher form symmetries to magnetohydrodynamics. Okay. So this is some work that I myself did with my collaborators, Sasha Grozdanov and Diego Hoffman. We're going to study the symmetry principle behind magnetohydrodynamics. So before I get into that, I want to ask everyone, what are the phases of matter? Okay. So I don't know about you, but when I was young, I actually learned that there are 4 phases of matter: solid, liquid, gas, and plasma. Okay. So solid, liquid, and gas, everyone knows about, but plasma is some weird thing, right? What is plasma? Okay. So plasma, in fact, if you Google the phases of matter, you again find that, you find solid, liquid, and gas, and plasma. So I always thought this was a bit weird. What's up with plasma? Why is plasma a different phase of matter? Solid, liquid, and gas, we all know, but plasma is some weird different thing. Okay. So, I see there's a question in the chat. The question says solid is supposed to have a larger symmetry than gas or liquid. Gas or liquid particles are completely random and hence less symmetry. That's correct. The solid has larger symmetry than gas or liquid. The reason is the solid spontaneously breaks the translational symmetry. And so there's some order there. The gas and the liquid are indeed completely random and have less symmetry. So the answer to your question is yes, that is exactly right. Indeed, ordered particles have a larger symmetry. That's exactly correct. Okay, good. Please keep the questions coming. It's much more fun for me if people ask questions as I go. But the question you might now ask is, what's up with plasma? What is the symmetry difference between plasma and between liquid and gas? Okay. So now I want to talk about that. Why is plasma a different phase of matter? So if you open your textbooks about what a plasma is if you have electrically charged particles, like electrons, positrons, protons, and so on, interacting together with Maxwell electrodynamics. Okay, so for example, you might have a positive charged particle here, a negative charged particle here. So it's a gas of charged particles, and they all interact with electric fields. This, for those of you who studied quantum field theory, is the Lagrangian describing it. If you've not studied quantum field theory, that's fine. Let me just tell you, this is the equation for describing how these systems interact. So you have a bunch of charged particles interacting via electric fields. So whenever you want to understand the system, you should ask, what are the symmetries of this system? And there are some symmetries for momentum conservation and so on. But what's particularly interesting is this system has a higher form symmetry because this has normal Maxwell electrodynamics in it, which means that the system has magnetic field lines and those magnetic field lines don't end. So there is a higher form symmetry associated with this. So let me now give you a very precise definition of what a plasma is. A plasma is a system in thermal equilibrium with a higher form symmetry. What that means is a plasma is a system in thermal equilibrium with a bunch of strings in it. And those strings are the magnetic field lines. What's interesting is this is not normally how plasma is formulated, but with this point of view, we can actually construct an effective theory to describe plasma. In other words, the realization of the symmetries at finite temperature defines a hydrodynamic theory. So what you do is you demand that you have a conserved stress energy tensor and a conserved magnetic flux tensor, and you demand that it be at finite temperature, and from that pops out a hydrodynamic theory, which is what we would normally call magnetohydrodynamics. So this is a novel and purely symmetry-based reformulation of this theory, which is what I constructed with my collaborators. What's sort of interesting is that it's in the right universality class of the theory in textbooks, but it's constrained only by symmetries in effective field theories. We never use Maxwell's equations when describing it. So that's interesting because you can use this in more places than the normal reformulation of Maxwell theory. So what do you get from this theory? So first, you get an ideal hydrodynamic sector. In other words, you get some sector that describes the dynamics of magnetic field lines moving in some fluid. But what's fun is that this theory depends on an equation of state, and it only is equivalent to normal textbook magnetohydrodynamics at weak coupling. In other words, if the pressure takes this form. So there is no symmetry-based reason for this separation. And in fact, our theory can also naturally describe plasmas that have strong electromagnetic correlations. So you can describe a larger class of plasmas with this theory. There's another question coming in. Are the fields which show symmetry always follow the equation of continuity? Excellent question. The answer actually is yes. Let me go back a few slides to answer that question. Basically, whenever you have a certain kind of symmetry, whenever you have a continuous symmetry, you will have a continuity equation like this one, okay? If you have a normal sort of U1 phase symmetry, you get a conservation law that looks like grad mu J mu equals to 0. If you have these fancy higher form symmetries, you will get a slightly fancier equation. You will have a continuity equation that looks like grad mu J mu nu equals to 0. So a symmetry always gives you a continuity equation. That is actually the content of Noether's theorem. Noether's theorem tells you whenever you have a symmetry, you'll always have a continuity equation. Excellent question. Thank you. Okay. So basically, whenever you have a symmetry, you can construct an effective theory. And in our work, we showed how you can derive an MHD equation from the idea of having a conserved stress tensor and a conserved flux tensor. Okay. So what can you do with this theory? So whenever you have a hydrodynamic theory, there's a certain transport coefficients in it, okay? So for example, in a normal liquid, you have viscosity. Viscosity controls the rate of diffusion of your system. So if you drop something into your liquid, the thing slowly spreads out. The speed at which this happens is given by viscosity. In the modern framework of hydrodynamics, such coefficients can be thought of as higher derivative corrections to ideal hydrodynamics. And in our framework, we can systematically classify all of these transport coefficients. It turns out there are exactly 7 transport coefficients in this magnetohydrodynamic plasma. Some of them are viscosities, and some of them are resistivities. Our framework lets us classify all of these transport coefficients. So here's another thing that you can do in our formalism. So imagine you have a bunch of magnetic field lines in your system. If you grab those magnetic field lines and pluck them, you see those magnetic field lines have tension, so they'll vibrate, okay? And waves will go down these magnetic field lines. These waves are called Alfvén waves, okay? And they're given by a magnetic field tension. And what you can do is, within our theory, you can find the equation for how those waves propagate. This is something that has been known for a very long time. They're called Alfvén waves. But our theory actually tells you the corrections to the leading order dispersion relation. So this formula here just tells you have a wave propagating down the magnetic field line. This formula here tells you how this wave dissipates or how this wave diffuses away. Notice there's some interesting angle-dependent dissipation. In other words, if you have your wave propagating at some angle to the magnetic field line, there will be some angle-dependent dissipation of this wave. This is actually a prediction of our hydrodynamic theory. So you can calculate it from our theory. Now, you can apply this approach to a problem in astrophysics. So let me take a step back and tell you about pulsars. Well, what are pulsars? So pulsars are objects that have a very, very strong magnetic field. Okay. Here I've drawn some magnetic field lines, and they also spin very, very, very fast. It turns out this creates a gas of free charges around the pulsar, and this is called the magnetosphere, okay? Because there's a very strong magnetic field here. The magnetosphere is full of both strong magnetic fields and free charges at 0 temperature. This is a Lorentz invariant interacting system. It's Lorentz invariant because everything here obeys the principle of special relativity. There is no preferred rest frame. So now, if you want to understand a pulsar, you might ask, how can I describe the strong magnetic fields here? So the usual approach is the following. Let me now tell you what the usual approach to this is. You assume that there are many different free charges. There are so many free charges that they perfectly screen the electric field. When I say screen, what I mean is the charges will move. If you have an electric field, the charges will move to neutralize that electric field. And what that means is that on long scales, the electric field is actually 0. However, the electric field is not a Lorentz invariant concept. So what you really mean is that the electric field in the direction of the magnetic field, E dot B, is equal to 0. But you nevertheless also assume that the charges are so dilute that they exchange no stress energy with the magnetic field. In other words, the magnetic field has so much energy compared to the charges that you can neglect the energy of the charges themselves. So this set of equations defines something called force-free electrodynamics. They're closed and highly nonlinear equations for electromagnetic fields alone. So this has again been known for a very long time, but there's a sort of observational problem here, which is that pulsars spit out things, okay? Pulsars create radiation, which we can observe on Earth. They also spit out particles. And this is interesting because if you want to have an observational mechanism for something where pulsars spitting out things, you require a non-zero accelerating electric field. In other words, you want to have an electric field that is parallel to the magnetic field. In that case, charges can move along these magnetic field lines. Which is weird because the normal assumption in dealing with these things is that the electric field parallel to the magnetic field is actually exactly 0. So in other words, to explain this, to create an interesting emission mechanism, we require a non-zero accelerating electric field. So we need something that goes beyond the normal framework, where this normal framework is called force-free electrodynamics. So this now is again a theoretical problem. What exactly is the small parameter in the force-free approximation, and how do we systematically improve on it? So here's a solution. What you can do is you can reformulate this as an effective theory using these higher form symmetries. So this is again what we did. We showed how to use these symmetries to construct a new effective theory describing this system. This is different from MHD because there's no preferred rest frame. Instead, the system is Lorentz invariant with respect to boosts along magnetic field lines. So you can boost your system, do a Lorentz boost along a magnetic field line, everything is invariant. And the way in which we constructed this effective theory was as a cold string fluid. In other words, the degrees of freedom are the transverse positions of the strings and a magnetic photon, B, that sort of carries the magnetic flux along each of these field lines. So you can again write down the most general effective theory that respects these symmetries. And if you do that, you find something very interesting. At lowest order in derivatives, you get force-free electrodynamics as the universal infrared theory. But the interesting thing is that you can now add higher derivative corrections to that. And these higher derivative corrections are basically morally equivalent to adding a viscosity to the Navier-Stokes equations. So these higher derivative corrections, they correct force-free electrodynamics in a systematic manner, and that results in new effects. So for example, in our theory, if you have a pulsar spinning with some frequency omega, this pulsar has not only a magnetic field, but also an electric field parallel to the magnetic field lines. And that results in a new term in your equations of motion, which can result in new observational consequences. So for example, this will now pull electric charges out and spit them out, and these may have observational consequences, which we're now trying to understand. Okay. So I see there's another question about the symmetries of solids. Let me just answer this question very quickly. The question says, solids possess a discrete symmetry only. In other words, solid breaks continuous symmetry. However, liquid has a larger continuous symmetry than solid. That is correct in a sense. The point is, the solid spontaneously breaks the continuous symmetry down to a discrete subgroup. Okay? So in a sense, liquid has a larger unbroken symmetry group than a solid. That's absolutely right. You see, you can see that. So you take a solid and you move it a little bit. By moving it a little bit, I mean you're acting on it with a symmetry operation. You're doing a translation on the system. It's a little bit different. You can tell with your eye. However, liquids are not. If you take a liquid and you imagine moving it, I mean, nothing happens. The liquid just stays a liquid. So that's how you can see that a liquid has a larger continuous symmetry than a solid. To be more precise, the solid spontaneously breaks this continuous symmetry. Very good question. Okay. So now, while we're talking about spontaneous symmetry breaking, let's return to ordinary symmetries for a minute. Let me remind you that symmetries can sometimes spontaneously break. So for example, if you have a bunch of particles in a box, and if the field describing these particles is all lined up, in other words, all of the phases point upwards, then this thing spontaneously breaks the symmetry What I mean is, if you do a phase rotation, it'll all rotate a little bit. In that case, this charged operator develops an expectation value. In other words, if you imagine averaging over these particle phases in some way, you can create a coarse-grained field phi, which is not equal to 0. Okay. So this charged operator now develops an expectation value. And when this happens, the long-distance physics is dramatically altered. Before telling you that, I see there's another question. Do the emission and absorption of one fundamental particle to another in quantum field theory is very similar to one string splitting into two in string theory? Yes, that is a very good question. It is actually true. If you have one string and it splits up in string theory, then there's a sense in which if you look at that from a great distance, that looks like a particle. You see, if you look at a string from a great distance, a string looks like a particle. If you look at the string splitting up from a great distance, it really looks like a particle splitting up and absorbing, emitting and absorbing. So there's a very precise sense in which the emission and absorption of strings in string theory is at long distances described by particle emission in quantum field theory. So yes, it is very similar, but string theory has more information than that in it. That's the right way to say it. So thanks for the excellent question. Okay, so basically, if you now have, imagine you have these particles, and there's an expectation value, in other words, meaning the symmetry is spontaneously broken. So all of these particle phases are all lined up in the up direction. When this happens, the long distance physics is dramatically altered. Let me explain why. So this is what I'm going to now tell you is called Goldstone's theorem. If you have a symmetry that is spontaneously broken, then it costs no energy to rotate things by the symmetry. In other words, if you have here this part of a bunch of these spins, and you rotate them all homogeneously, this costs no energy, right? Because this is a symmetry of my system. In other words, what that means is, if we now imagine rotating it not exactly the same way everywhere in space, but you imagine modulating this thing a little bit in space. In other words, I rotate this guy, then I rotate the neighbor not exactly the same way, the next neighbor not exactly the same way. In other words, I modulate the symmetry over some long distance scale, which I'm going to call K inverse. Then the energy is 0 as K inverse goes to 0, which means the energy now grows as some power of the wavelength. Okay. And as you get K to 0, this situation here becomes that one, and the energy goes to 0. In the quantum theory, what this means is that you have an excitation which costs very little energy as the wavelength goes to infinity, as the wave number goes to 0. These gapless excitations are called Goldstone modes. Okay. So it turns out Goldstone modes appear everywhere in nature because they are one of the only ways to get a naturally gapless excitation. Let me start with a solid. Here the symmetry is translational symmetry. And it turns out there's a vibrational mode which propagates through the solid. This vibrational mode comes from the fact that there's a translational symmetry. So the crystal vibrations arise from that. In other words, sound is a Goldstone mode associated with spontaneously broken translational symmetry. If you have a superfluid which spontaneously breaks this U1 symmetry, here's a plot of the energy of the superfluid dispersion with respect to the wave number. You can see this thing goes down here and hits 0 as K hits 0. This is a superfluid excitation called the phonon. And again, it's gapless because of the spontaneously broken U1 symmetry. And finally, in elementary particle physics, we have a symmetry called SU2 left cross SU2 right. This is the chiral symmetry of quantum chromodynamics. This is a very fancy symmetry, but it is spontaneously broken in nature. It's not an exact symmetry. So its spontaneous breaking doesn't give us an exactly massless particle, but it gives us a particle called the pion, whose mass is very, very close to 0. This is very, very close to 0 because the pion is actually a Goldstone mode of a spontaneously broken symmetry associated with this abstract SU2 left plus SU2 right symmetry. So the point of the slide is to show you that in nature, many things are Goldstone modes. There's really a sense in which sound, this sound by which you hear me right now, is a kind of Goldstone mode. Okay. So these higher form symmetries that I've been talking about can also spontaneously break. But remember I told you the charged object for a higher form symmetry is not a local operator. It's instead a string operator. In other words, it's an operator defined on a closed curve. So what happens now is that you should imagine you have some sea of strings all sloshing around in some complicated way, and they slosh around in a particular manner in which the charged line operator, in other words, the VEV, the expectation value of W of C, is not equal to 0. If this charged line operator develops an expectation value, this corresponds to a string condensate. In other words, there's some sea of strings sloshing around. And when this happens, the long-distance physics is dramatically altered. There's another question: why do techniques of quantum field theory fail for the fourth fundamental force, which is gravity? That's again a great question, but it's a little bit away from the topic of what I'm talking about right now. So if it's okay, Abhinav, I'll answer that at the end of this talk. All right, I'll answer your question. Okay, so let me now proceed with this. So basically, the point is these higher form symmetries can also spontaneously break. And when they do, it turns out you also get a massless particle. So I proved this with Diego Hoffman. What we proved is that if you have a higher form symmetry which is spontaneously broken, then you can show that there's a certain correlation function between two operators in your theory, where that correlation function decays as a power law. What this means is you insert a line operator in your system, and you imagine looking at the correlation with a certain local operator, and as you take this further and further away, this thing decays like a power law. This power law turns out to imply that there is a gapless excitation in your system. And in other words, you have a gapless mode. So what this means is you have a bunch of strings all sloshing around in your box. If you want to ripple this sea of strings in a particular way, then certain long wavelength ripples of the string cost very little energy. So this is a Goldstone mode, which is a mode associated with long wavelength ripples in this box. So let's return to this theory that we talked about for a long time, Maxwell electrodynamics. What you can do is you can calculate the order parameter for the spontaneous symmetry breaking within this Maxwell electrodynamics theory. And what you will find is that the expectation value of this order parameter goes only as the perimeter of the length of this curve, which means that this symmetry is actually spontaneously broken, and there should be a gapless Goldstone mode associated with it. In this theory, the Goldstone mode is actually the ordinary photon. In other words, the reason why the photon, in other words, the light by which you can see me, is a massless mode is because of Goldstone's theorem, but for higher form symmetries. So what that means is we should really add the photon to our list of gapless modes here. The photon is gapless because it is a Goldstone mode for a spontaneously broken higher form symmetry. Okay. So this was most of the science content that I wanted to give. So now let me just conclude very quickly. So here are a few future directions that we can think about. I've told you about some new effective theories, and you can now ask, what are the observational consequences of these effective theories? And you can, in particular, this force-free electrodynamics that I told you about is very interesting because I'm really hopeful that this can help answer some questions in pulsar physics. We are currently actively investigating this. When I began this talk, I showed you this picture of this guy Landau, and I told you about the old Landau paradigm. The Landau paradigm tells you that there are phases of matter with different symmetries. You should now ask, what is the new Landau paradigm? And does it include, for example, topological phases of matter? Topological phases are interesting new phases of matter that are not normal solids, liquids, or gases. And it seems that some of these can be understood in this way, and we're trying to understand which ones you can understand precisely. And finally, in nature, there is exactly one more gapless boson, and that's the one associated with gravity. You see, gravity is a long-range force. And if you think about that in the quantum theory, you have a massless particle called the graviton. And I'm very interested in understanding whether the graviton can be understood as a Goldstone mode. As Abhinav asked already, the techniques of normal quantum field theory fail for the fourth fundamental force, for gravity. And that's really because gravity behaves very different from all the other forces. I can answer this in a bit more detail at the end of the talk. But basically, gravity is very different. And I'm very interested in understanding if the graviton can also be understood as a Goldstone mode. OK, so let me just conclude with a quick summary. To summarize, symmetries in effective theory are a key organizing principle understanding nature, and higher form symmetries are a new kind of symmetry that has to do with the conservation of extended objects. These can be used to build new effective theories that present new ways of thinking about real-life problems. And theoretical ideas like the Landau paradigm, Goldstone modes, and something I didn't quite tell you about called bosonization take on new life when they're combined with these new symmetries. That's what I want to tell you, so thank you very much. That's the end of the science part of the talk. And I want to give you one more takeaway lesson. I began this talk by talking about some sort of strike. Let me just tell you what's happening. In the UK right now, thousands of lecturers all over the UK, including me, are actually not giving normal talks and not lecturing. I gave this talk because it's a bit special to people in Bangladesh. But basically, most of us are not lecturing right now. And the reason is that there is some dramatic cuts happening to the pensions and to our pay. If you're interested in this, I do encourage you to Google the words UCU strike, and you can find out what's happening in the UK right now. Okay, thank you, everybody. That's the end.
Yeah, thank you, sir. অনেক অনেক ধন্যবাদ। আমরা মনে হয় দুটো কোশ্চেন বাদ আছে।
Okay.
We can talk.
Yes. So the first question is, why do the techniques of QFT fail for the fourth fundamental force, which is gravity? Okay, that's an excellent question. Let me explain why. So gravity is a little bit different from all the other forces. And there's many ways to understand it. Gravity is the curvature of space and time, and that's very dramatic, and that's very different. There's a sort of more particle physicsy way to explain this. Let me explain why. You see, if you have two objects and they feel gravity with each other, the way to think about this in quantum field theory is that these particles exchange gravitons. Okay, so they're gravity particles called gravitons going back and forth very, very quickly. But you see, gravity couples to mass, and we know from Einstein that E equals to mc squared, so gravity and energy are kind of the same thing. And so you see these gravity particles going back and forth. You see they have mass and they have energy. So they themselves feel the force of gravity. So they create more gravity particles, okay? And then those gravity particles create more gravity particles. And there are more and more and more gravity particles. And there are so many gravity particles that you basically can't make sense of this anymore. So technically, this means that gravity is non-renormalizable, okay? It means that quantum field theory for it does not work if you look at short distances. And that's why quantum field theory at short distances does not work for the theory of gravity. It's because there are too many gravity particles at short distances, okay? And the fancy way to say that is to say that gravity is non-renormalizable. So you can Google that word. The next question is, can neutrino oscillations be explained in quantum field theory? Yes, they can. They can be explained in quantum field theory. They cannot be explained in the standard model of particle physics. You have to take the standard model of particle physics and add some new stuff to it. And if you do that, you can explain it, but it's still a quantum field theory. It's just not the regular vanilla standard model. It's standard model with a bit more stuff.
ওকে স্যার, অনেক অনেক ধন্যবাদ। অসাধারণ আমরা একটা লেকচার শুনলাম এবং ডিসকাশন সেশনের জন্য আশা করি আমাদের স্টুডেন্ট এবং দর্শক উপকৃত হয়েছে। তো আমাদের বিভাগের পক্ষ থেকে আপনাকে আবারও ধন্যবাদ। Thanks again, and hopefully in near future we can arrange another webinar with you, and hopefully we can invite you in our campus directly for a face-to-face session.
I would love to. Please invite Corin. Pandemic situation.
একটু কমলে তখন করব।
Please. Okay.
So ভালো থাকবেন।
Thank you.
Bye.